Welcome to the lightning round, Representations in Deep Learning Systems. Our first speaker is Fintan Mallory from the University of Oslo. He's on a postdoc there. He can't make it in person, so it's been arranged that he can do it through Zoom. So everyone please welcome Fintan, Teleosemantics for neural word embeddings.
Hey, okay, great, thank you, and welcome from Oslo. I'm sorry I can't be there. I think I'd probably have to be more apologetic if I turned the conference into a super spreader event. But I think Raphael has offered to buy a pint for everyone at the conference on my behalf, which is just a lovely thing to do, so thanks for that. Okay, great. The first thing I should probably engage with, if this slide starts operating, is the false advertising that this is a conference on the philosophy of deep learning, and I've literally brought Word2Vec here. Word2Vec has 3 layers. It's not really a deep learning system at all. It is about as shallow as you can get. But I want to make a case in this talk for good old-fashioned incremental theory building. That is methodological incrementalism, by which we try to develop theories for representing what's going on in the simplest systems, and then we incrementally extend them in order to handle more complex representations as the theory gets more complex. I think that this is desirable for many reasons. One is that we can understand the novel additions that more sophisticated computational devices enable us to achieve. But on another level, if we want to understand the history of the field, we need to begin with where a lot of the recent work on neural language modeling began, and that's Word2Vec, which was one of the first widely implemented systems. This is also, I'm just flagging, a part of a wider project of mine. If you're interested, my website's at the opening slide, or get in contact with me. I'm over here in Oslo. So what do I mean by having a theory of representation for deep neural networks, and specifically large language models in this case? One, I'm assuming that there is an objective fact of the matter about what a network represents, and that's the kind of thing that we want to study and be able to understand. I take it that there are a couple of reasons that you might be interested in this. If you're interested in things like artificial general intelligence, then you're going to want some kind of condition for distinguishing between the actual original intentionality of an artificial intelligence from things that we are merely attributing to it or misinterpreting or finding in it. Alternatively, if you think that in some sense semantic internalism of some form is true, and you think that our interpretation of the content of the text generated with large language models should be constrained by the internal representations that those models possess, you're going to want to have a theory of representation for those internal representations. I'm going to assume that there's roughly 3 desiderata on a theory of representation here. One is that it can explain the role that representations play in the operations of a system. We can say, oh, well, the language model produced that output because it represents the world as being in this way. A second is that it can constrain the kinds of contents or representations that we ascribe to the model. That is, again, as I was mentioning, we don't want to be reading too much into these models. We don't want to be attributing them representations that they don't actually possess. So having a criterion for saying this is a genuine representation versus this is a spurious representation seems to be a desirable thing. And a third element is just we want to unify the methods of probing that currently exist in the literature. Anders Sigurd, who I think is also speaking at this, has a wonderful recent book. I mean, recent in so much as we can speak of recent literature in this field, that highlights just the diversity of different probing paradigms that exist out there, from closed sentences to probing classifiers and lottery tickets and pruning attention heads. We assume that they all get at something, which is the representations within the systems, but figuring out how all these different methods hold together and tell us about the same thing is something that the theory of representation should be able to tell us about. Now, slightly more controversially, and also old-fashioned, I'm going to be assuming something like a minimal form of teleosemantics. If you don't like teleosemantics, if you don't think teleosemantics is the right way for understanding human cognition or representations in the central nervous system, that's okay. Hear me out for making the case for teleosemantics in the case of very simple neural networks. Secondly, I'm not going to be making any claims like that teleosemantics gives the right account of the linguistic outputs of either humans or any of these machines. I do think it can shed some light, however, on what's going on in Word2Vec. I'm not going to be hitching myself to any particular development within the teleosemantic tradition. I'm going to try and keep a lot of these claims as ecumenical and broad as possible. What I'm going to present is going to be a largely consumer-based account, of teleosemantics, but if you like Nick Shea's Veritalesemantics, that's great. I do too. If you like Karen Neander's informational teleosemantics, that's great. I do too. It's a diverse field, and that's one of the virtues, I think, for taking it as a framework for understanding the representations in these systems, because it's not entirely clear that one framework is going to capture every single possible language model or that we have at the moment. For the purposes of this talk, I'm going to reduce it to 3 broad claims, 3 general claims, G1 to 3, and then one particular claim that's relevant for this case of Word2Vec. The general claims are that systems contain mechanisms for producing and consuming representations. The second general claim is that the contents of those representations are determined at least in part by the functions of those mechanisms. And the third is that function in this case needs to be understood in some broadly evolutionary sense, such that there has been a process of selection over time. The particular claim that I think is relevant in the case of Word2Vec, and that is slightly more controversial, is that some simple systems have a form of representation that Ruth Millikan calls a push-me-pull-you representation, one for which our notions of descriptive and directive content aren't really separable. By directive content, I mean something like an instruction or an imperative signal that it sends to the consumer system, like a blueprint. And by descriptive content, I mean the condition under which that direction or instruction is successful. So the classic example in the literature is a hen's call indicating both come here and eat and there is grain here. It has both the direction and the description built into the same content. And Millikan's interesting suggestion is that only in more sophisticated systems do we actually manage to pull these apart and have purely descriptive representations. I hope by the end of this talk, I'll have indicated one way in which work on deep learning at the moment can shed light on that. Now to Word2Vec. Well, actually, I should say the questions that I'm trying to answer first. I'm pre-regging. The questions that we're going to be interested in are, what are the mechanisms that produce and consume these representations? And we're hoping that teleosemantics can shed a light on that. What are the functions of those mechanisms? Can we appeal to those functions to describe constraints on what is represented, the representations we attribute to these systems? And does the framework make sense of any further semantic claims about the system? This is one that's closer to my heart. By further semantic claims about this system, I mean the kind of why side to the computational level explanation that you get within the Marian framework. That is, after we've identified what mathematical function is being computed by the network, can we say why that is the function that is being computed? And that's what I'm treating as a further semantic claim. Okay, now to Word2Vec. And you can see that I am indebted here to the work of the late Jean Rong, as I think everyone that works on Word2Vec really is. This graph or diagram was taken from his influential introduction to Word2Vec, and all I have done is turn the W's upside down to make them into rather implausible M's. That's M for matrix, M for mechanism, because I'm treating the weight matrices as being the mechanisms which evolved during the process of backpropagation. Now, very, very quick overview here of the simplest possible way that you can set up Word2Vec. I'm not going to cover skip-ground negative sampling in this talk. I mean, we can discuss it in the Q&A if you like. I know it's what everyone likes, but I think a lot of these claims are going to generalize to more richer versions of Word2Vec. All I want to do is give a very simple introduction to a continuous bag of words model that takes a one-word input and is tasked to predict the next word in the data set. So there are 3 layers, as I mentioned, to Word2Vec here. We've got the input layer, which takes a one-hot encoding vector of a word from the lexicon. By one-hot encoding vector, I just mean it's a vector with lots of zeros, except for one dimension that is marked out and identifies what the word is. It then, it then processes that through the first weight matrix to produce an embedding vector, which is projected into the hidden layer. And these are going to be the word embeddings that we're interested in developing through the process of training. And then that word embedding is fed to M prime, which is going to be our consumer system. And that consumer system is going to output, after the application of a softmax function, a probability distribution. Now, I'm going to flag now that I've just made the first semantic claim. The first thing I want to just flag is we have 2 mechanisms here. We have a producer and we have a consumer, M and M prime. These are the things whose evolution we're going to want to understand. But I've also made this further semantic claim, or at least I construe this as a semantic claim. Calling the output of a softmax a probability distribution is, as I understand it, a semantic claim. It's a claim about how the output refers to the world. Lots of things add up to the number 1, but that doesn't mean that we should interpret all of them as probability distributions. Softmaxes are used all over the place these days in machine learning, and often we don't call their outputs probability distributions. That further claim has to be earned, and I think a theory of representation should play a role in explaining how it is earned. Second, if you're interested, yes, this isn't the standard process of evolution, but gradient descent actually satisfies the standard teleosemantic conditions on a replication process. That is, each stage, the weights that are altered during the backpropagation process are similar to how they were before. They counterfactually depend on how they were before, and the update is occurring in a nomological fashion according to a natural law, or in this case, as you see in the bottom right, the update function. Now, during the process of backpropagation, what is output? This is the semantic claim, is a probability distribution that is compared to the actual data, and the distance between that is computed. You know how this works. It's fed back, the weights in the system are changed, and as a result, M and M prime alter their internal structure in order to be able to perform their job more effectively. So we have two mechanisms that are undergoing a process of evolution in order to produce representations that allow the second mechanism, the consumer mechanism, to perform its task more effectively. Now the representational claims. There are a lot of representational claims we can make about the resultant embedding spaces that you get with Word2Vec. I'll just run through the 5 normal ones, and each of these seem to correspond to different levels of mathematical complexity or mathematical abstraction. One is what you have at the end is a set of word embeddings, that is a set of vectors that seem to correspond to the items in the vocabulary. And you can compute cosine similarity between these vectors, and that seems to correspond to something like semantic similarity. That's why the system was developed in the first place. A second thing that Nikolov discovered in the original Word2Vec paper is that these vectors can be added and subtracted. So the classic example is that you can take the vector for king, subtract the vector for man, add the vector for woman, and the location you end up in is somewhere like the vector for queen. And so you might then say on another level, oh, it's representing conceptual relations that it wasn't trained to discover. A third kind of trick you can play is to use linear transformations to capture scales. So Gabe Grattan has shown a way that you can plot a line, well, okay, like a 300-dimensional hyperplane, a fancy line, between antonyms in the embedding space, and find a linear transformation to map entities within that vector space to that line, such that it seems like we can say the system is also representing scale. And it's not just for small and large, it's for dangerous. I really recommend the paper. It's a beautiful paper and a really interesting result. It's technically, I think, using GloVe rather than Word2Vec. But again, a very simple, very, very simple neural language model. Another kind of representation that you might think you found in Word2Vec is what I call a PCA map. So one thing you can do is you can take these vectors that are like 300 dimensions, you can reduce them to 2 dimensions with principal component analysis. And hey, look, as I think this is a fairly familiar example, whenever you ask for the locations of European cities according to this 2-dimensional vector space, you get something like a map of Europe. Do we want to say that the word embedding model represents this? Because in a sense that it is part of the content, it is an original representation rather than just something that we're reading into the system. A theory of representation should give us an answer to this. And finally, whenever you're done, you can run a linear probe over these things and see if they track something like numerosity. These are all different possible kinds of representational content we might find in Word2Vec. What I want to do next is to ask, well, look, are these intentional representations according to a system like teleosemantics? What is it to give a teleosemantic analysis of the system? Well, we're just going to look at it. We're going to consider it in these evolutionary terms, and we're going to ask what is being produced and why is it being produced and who is producing it. We'll start like consumer teleosemanticists at the output layer. At the output layer, We have the mechanism M prime that is generating a probability distribution. And this is where we have the answer to the softmax question earlier. In virtue of what can we say it's a probability distribution? We can say that it's a probability distribution because the mechanism has evolved to produce a probability distribution. That is what it is tested against during the process of backpropagation. That is what the mechanism M prime has evolved to produce, or has been altered in order to align with. Knowing that, we then reach the interesting push me, pull you level. The word embeddings themselves seem to have both directive and descriptive content. On the directive level, the word embeddings seem to provide instructions to M prime, our consumer mechanism. The embeddings seem to provide instructions or a blueprint for generating probability distributions. So that's the directive content. It's what it's telling the later system to do. But it also has the descriptive content such that ultimately over the process, it has also, the mechanism M has evolved in order to produce distributions that better accord with the distributions that are actually in the data. Therefore, it has the descriptive content of tracking the distributions in the data. And the one hot encoding layer, I'm merely highlighting because I think there's a stupid question we don't often ask. Why don't we say that word embeddings represent their one-hot encodings? And it isn't simply because I'm not sure that there is much empirical work to see if you can reconstruct one-hot encodings from the word embeddings. But I think the deeper reason is that the word embeddings, like many representations, as Dretske highlighted many years ago, pass through these most proximal stimuli in order to latch on to what they are representing in the world. I think it is an empirical question as to whether or not, in some sense, they represent those that encoding layer, but we have no reason to believe that they actually do, which also gives us further reason to believe that they represent something more distal than that. Now, if this is correct, then I have given a really conservative result because I've listed 5 different kinds of representational content we might ascribe to a system like Word2Vec, and then I've said, actually, all that's being represented is distributions in the data. At least that's what the teleosemantic framework seems to be suggesting to us. At the hidden layer, we have our word embeddings that are directions to produce a kind of representation. And in virtue of being so, they are also therefore serving some kind of possessing some kind of descriptive content that is the representation, that is the actual distribution in the data. Now, that's fairly conservative, but I think it begins the process. And this is, again, the very first step in this, by which we can begin to ask further questions about what it would take in order for a language model to have purely descriptive representations. So everyone likes it when philosophers make conjectures. I want to end a kind of conjecture here. And it is, at what point does the system, it is an answer to the question, at what point does the system go from representing mere distributions in the data to representing something like the relations that I highlighted in the first 2 possible kinds of representation, that is cosine similarity and internal conceptual structure. I think that it goes, that the system goes from having purely push me, pull you representations that represent distributional structure to representing more rich structure whenever you have something like attention heads. And it is that, in virtue of having attention heads, that makes the further structure that exists within the representations exploitable. So that, I realize I've actually come in within time. That's great. I will wrap things up there because I don't want to hog everyone else's time. If you are interested in this project, feel free to drop me a line. If you hate it, also feel free to drop me a line. I'd like to hear all the things that are wrong with it. Thanks.
So we actually, Fintan, as I understand it, you cut in into a little of your question and answer time. So we only have about 5 minutes. Yeah, no, that's, I mean, we were glad to hear it, but we only have 5 minutes, I think, or so for questions. Who's got some questions? Yes.
Thank you for your talk. Do you hear me?
Yeah,
okay.
yeah.
What do you think about the emergent functions that were not intended in the original training of any of these sort of large language models? Well, Word2Vec would be a small language model, but all of the language models, there's a lot of emergent functions that were not intended. It wasn't intended for consumption. However, in the training set, which includes text by humans, there were some other functions intended that's not in the objective function of the LLM. How do you address that with your teleosemantics?
So I think one of the virtues, so I think one, you've hit on what I think would be traditionally regarded as a problem with this, which is that teleosemanticists generally regard the function of artifacts like neural networks as being determined by the intentions of the designers. I don't actually think that that is going to be, I don't think that that holds up in the case of neural networks, where we don't actually, like, our intentions whenever we train a network, we try to get it to do what we want, but often it will begin, like if it serves the method of training to develop representations that we weren't intending for it to track, then I think in that case, our intentions at least don't really matter. I think that the teleosemantic framework can give some kind of indication as to how these networks can develop representations that are not what we intended. I don't feel like that's an adequate answer to your question, though. Like, I think I should also flag the 5 things that I noted earlier, the 5 layers of representation. I'm fairly sure the only thing that Nikolov highlights in the original 2013 paper that they're aiming to capture is semantic similarity in accordance with a kind of cosine similarity metric for the vector space. Nothing there is mentioned about capturing conceptual relations like the man-king one, or anything about PCA maps or the linear projections that Gabe Grants discovered. All of that was unintended layers. But I don't think, because it's not used for downstream computations, we can really say it's a representation within the system, in accordance with teleosemantics, at least.
Yeah, thank you so much. So I just had a curiosity as to what you think the actual contents of the output layer are. So usually when you put forward a teleosemantic theory, you're trying to answer the question in virtue of what does this internal state represent this distal property or something like that. Yeah. But when you went to go describe how your theory worked, you seem to suggest that the output layer represents something like softmax or a probability distribution. So I was just wondering if you could clarify how that relates to the standard way of understanding teleosemantic theories.
Yeah, absolutely. So one thing is that I think that, an important thing is that whenever I say that the output layer represents a probability distribution, I think I'm making a fairly strong claim there. I think it's often treated as being a light claim, like a weak claim, because we just say softmax outputs probability distributions. And I think that that's a kind of further semantic claim that has to be earned. I would suggest that it represents, the output layer represents a probability distribution over, in this very simple bag of words model that I'm showing here, or I'm using today. I would say it represents a probability distribution over the most likely next word. But the reason, or at least the argument for why that's the case, is simply that the mechanism M prime, the consumer mechanism, effectively has the function in the teleosemantic sense of producing probability distributions, because probability distributions are what it is assessed against in the training.
Okay, thank you. I want to ask, where are you based in, to separate the different stages and say that its matrix, connectivity matrix, is a mechanism that is separate than the other, because as far as I understand, mechanisms in a neural network is a result not only of the connectivity matrix, but also on how the units are connected, say the structure of the differential equations that relates the units with the matrix. If it's a linear differential equation, it's easier to just look at the matrix. But if it gets more complex, it's not that straightforward, and especially if you have different levels, which makes sense to look at it as a whole, as a system. So how I don't know how you separate them.
Yeah, that is a brilliant question. I think that, and this is like, so in one sense, the incremental approach that I'm taking, like all of the difficult questions like that, I see as being things that are coming up in the future. In the case of Word2Vec, I think, yeah, the first layer is purely linear. And so that's how I individuate the mechanism, by just saying that, like, we treat the matrix as the mechanism. In the second mechanism, it has that softmax, but again, you know, every like the entire output vector from that softmax is feeding into the output layer, and so I would individuate it in that sense. But yeah, I think in much more, like in more complex systems where you've got like multiple attention heads and you're trading on lots of different information, it will not be possible to just do this one-to-one matrix to mechanism account. And so no, that's like an important question. I'm not sure it causes a problem for the teleosemantic approach to Word2Vec, but it's definitely going to be an interesting empirical challenge whenever this is applied to richer systems or more sophisticated systems.
Okay, thank you, Fintan. We should cut it off there. Let's thank Fintan. I'm going to try to be pretty strict. Of course, remember, you'll have opportunity. I'm sure you'll be eager for follow-up. But meanwhile, our next speaker is Jacqueline Harding. She's in her second year in symbolic systems at Stanford, and she's going to be speaking on do probes and natural language processing discover representations.
So yes, I'm a PhD student in symbolic systems at Stanford. I'm advised by Rosa and also by Thomas Eickhardt. And today I'm going to present a small part of a larger project. It's definitely a very lossy compression of the larger projects. The aim of the project basically is to present some hopefully plausible criteria on assessing representational claims as they're made in NLP, and then take some first steps towards operationalizing them. So this is kind of a philosopher's operationalization. So it's still very idealized in ways which we can hopefully draw out in the Q&A. I just want to make a clarification at this stage. There's a kind of thinner sense of representation in the vicinity here, which is ubiquitous in NLP, where any intermediate state of a model counts as representation. That's not the sense I'm using here. I'm using it in the sense it's used in kind of philosophy of cognitive science. Still quite a thin one, subpersonal representations. Okay, so here's some motivation for the project. Suppose we're testing a model on the COLA task. COLA is just a binary classification task. The model takes a sentence as input, outputs, whether it's grammatical or ungrammatical. And suppose the model is processing the following input. John dances waltzes across the room. So this is grammatical. We can imagine two different cases, one where the model gets it right and one where it gets it wrong. Contemporary models are going to get this right. So if it gets it right, maybe we want to explain why it got it right. And we want to say something like, oh, it's representing the dependency structure of the input sentence or something like that. And if it gets it wrong, maybe we think about why a human might get that wrong. And we say, oh, it's misrepresenting the part of speech of the word waltzes. So it thinks waltzes is a verb when in fact it's a noun here. The point isn't that the explanation is true or even plausibly true, is that it presupposes a notion of representation. So it's really just that it's plausibly truth apt. And the question then I'm concerned with is, what does it mean for a component of a model to represent a property of the input? So here's the general setting I'm considering. We have a system S performing a task D. I'm going to think of a task for simplicity as just a set of inputs with some associated goodness measure on outputs. So that could be a loss function. The abstract picture is as follows. We have inputs, which are encoded as intermediate activations. I'm going to call that just a d-dimensional vector, and then mapped by a downstream system, SDEC, to an output. So more concretely, we could think of the system as like a transformer. Inputs could be a list of token IDs. This intermediate activation could be the value of the residual stream at some layer and position in the context window. And then the output could be a probability distribution of the tokens. So two more notes on terminology. So when we process the inputs comprising a task, we'll get an intermediate activation for each input. And this will result in a pattern of activations across the task, which I denote H of big D. We're interested in properties. So I'm going to treat a property as just like a finite set of labels. So some examples of properties could be part of speech tags, dependency heads. We could have sentence level properties, like whether the subject of the sentence is singular or plural. We could even have more kind of high level semantic properties, the gender of the subject of the sentence. I'm assuming that each input is associated with a gold label distribution over the property labels. So this big P of Z is just a set of probability mass functions over this finite set of labels. So I'm going to assume that the kind of natural vehicle for representational claims in this setting is the pattern of activations, HD. And I'm just going to briefly give 3 criteria which seem relevant for assessing representational claims in this area. I'm intending these criteria to be amenable to lots of different ways of fleshing out representation, but they do have this kind of broadly teleosemantic flavor. So maybe it's good that Vincent just spoke on this. So the first criterion is that the pattern of activation should bear information about the property. The second is that the information it bears about the property should be used by the downstream system to perform the task. And then the third criterion is that this account should allow for an activation to misrepresent the property with respect to an input. So just as we want to use representation to explain success, we want to use misrepresentation to explain failure. Okay, just to briefly introduce like the probing paradigm, I assume this is familiar to many of you. The setup looked like this. We had an input mapped to an activation, mapped to an output, and then the input was also associated with this gold label distribution over property labels. So what we do in probing is we try to train a supervised classifier to predict the gold label distribution directly from the intermediate activation. So we just use labeled pairs to do this. So the classifier takes in an activation and it predicts a distribution over labels. We say a classifier is successful just in case it achieves like low cross entropy loss on some test set. And this suggests a natural way of operationalizing the information criterion. We just operationalize it by saying we can train a successful probe for the property. So this is a pretty cheap success. We could make this more formal in terms of something like mutual information, but hopefully it's intuitive that this is what's going on. So moving on, it's much harder to think about how we should understand use and misrepresentation. What I want to say about these is that the right way to understand them is causally. So we want to think about if we could do the right sort of intervention on activations and measure its effect on the downstream system, this would be a way of testing a use claim. Now, what's the right sort of intervention? Well, here's a kind of intuition. What we want to do is we want to intervene on the activation with some input to strip it of the information it bears about the property, fixing how the downstream system is using that information. But we want to leave it otherwise unchanged relative to how the downstream system is decoding the pattern of activations as a whole. And if we did that intervention and the system was in fact using the information, we'd expect its performance on the task to degrade. So the problem with this picture, of course, is that the downstream system isn't explicitly decoding the information in the pattern of activations at all. It's doing, to the extent it's interacting with the information, it's doing it kind of implicitly. We'd love to be able to write the downstream system as the composition of something like a probe and then some other model which takes the predictions of the probe and produces some output, but we can't. And in a sense, this is what motivates the whole probing paradigm. It's that we use probes as proxies for the sorts of things the downstream system could be doing to the information. So we can use this insight to operationalize the intervention at hand using probing. So just some terminology. This big set GZSDEC is going to be the set of probes for a property compatible with the downstream system. So this is kind of vague. What I have in mind is something like the downstream system can implement these probes. That's also quite vague. We'll think of like the probe selection criteria as further refining this set. But just to give a more concrete example, if the downstream system is linear, we want this set to only involve linear probes. We don't want them to have non-linearities because then the downstream system couldn't be doing what they're doing. And so this is going to be a bit notation heavy, but I'll just try to get the intuition. So an intervention is just a function on RD, and I'm saying it has to satisfy 2 criteria. So The first one is relative to any successful way of decoding the information that is compatible with the downstream system, this intervention should push the predictions of those decoders, those probes, towards the uniform distribution over the property. And then the second condition is that it should kind of preserve the predictions of other decoders for other properties. And that kind of closer and preserve, I'm just suggesting we could operationalize using KL divergence. So having defined this intervention, we can give a natural operationalization of the use criterion, which is just we have an intervention of this sort, we apply it to an activation, and if in fact the downstream system was using the information about the property, its output should degrade relative to the task. So how to understand misrepresentation? I want to understand this quite similarly to use. We test claims about misrepresentation by applying the right sort of intervention on activations and then examining their effect on system behavior as a whole. So again, here's a kind of first attempt just to pump some intuitions. Intuitively, what's going on in a case of misrepresentation is the downstream system sees the activation and it interprets it as saying something false about the property label distribution. So in theory then, if we could intervene to make the downstream system believe the true thing about the property label distribution, then this would improve its performance on the task. This is just an intuition, of course, for the reasons I just gave. Like, we shouldn't think of downstream systems as doing anything like this. They're not looking at activations and trying to directly predict property label distributions at all. But maybe we can use things that do, probes, as proxies for the sorts of ways the downstream system could be interacting with the information. So again, we have this true label distribution, and then we can define what I call the correct intervention. So a correct intervention is basically just the same as an ablate intervention, except rather than satisfying the ablate condition, which pushed predictions of successful probes towards the uniform distribution, here we want the predictions to be pushed towards the true label distribution. And again, we want to control for other properties and other probes. And obviously, the task of controlling in this way is incredibly difficult, and it's something that can be drawn out in the Q&A as well. So having done this, this suggests an actual operationalization of the misrepresentation criterion. Again, we have this correct intervention, we apply it to an activation, and then we see if the system performance improves relative to the task. And the thought is that if it does, this provides some evidence that the system was misrepresenting, or specifically the component HS was misrepresenting the property for the system. So here's a summary of where we're at so far. I'm saying we should think of representation as just, we can train a successful probe, we can apply the right sort of intervention to test for use, and then we can apply the right sort of intervention for misrepresentation. And so kind of some obvious issues with the account I've proposed are, firstly, how should we understand the set of probes compatible with the downstream system? And here there's a very large literature on probe selection, which we can get into. But I imagine questions in that literature will bear upon how we select this set. And then the second, I think, main issue is to do with controlling for various properties. And we can talk about ways that we could maybe start to think about that. And there are some examples, I think, which provide approximations of the account I've suggested in the literature, which again, we can get into more in the discussion. Thanks so much, and I'm looking forward to your questions.
Thank you. Anders, if you could start getting set up. Oh, you have a question, but we'll go to you first. Maybe we'll get to your question as well, Anders.
Yeah, thank you for the wonderful presentation. So when you talk about this approach, I'm thinking out loud on exactly the paper on Othello. And I mean, we are working on something on this as well. But so do you imagine implementing this concretely? For example, in the Othello, you do some control of the probes more carefully and actually claim something about the world representations. And second question is, I think, you know, along the line of the representations, the hard question is, I mean, to control the probes well is already hard, but I think another hard question is like to ask what kind of representations the probe is going to select, right? Like so far, I think it's easy to say come up with Bohr states and certain concepts like diagonal, certain things. It's hard to say it represents, say, you understand the rule of flipping the chess pieces, so on and so forth. So how do you think about that? So that's, I guess, two questions. Sorry,
Yeah,
it's too greedy.
There are two questions there, which I think are both really good ones. So yeah, I think I've been talking about probing as it's used in NLP, but of course, everything I said here could apply in principle to any model with intermediate activations. So I do intend that some of the thoughts here could generalize to other settings, although of course we'd want to make modifications. With respect to the question of basically how do we select which properties to probe for in the first place, or how should we think about the property the probe finds? Yeah, here my view is quite close to the account that Rosa outlined earlier. I think the sort of representational claims we'll want to make will earn their keep by allowing us to make robust predictions. And so to that extent, I think the sorts of properties we'll want to pick out are the ones we think are plausibly relevant to explaining system behavior across a range of inputs. And of course, spelling that out in a given domain is an incredibly difficult task and should be viewed in that way. Just to say one more thing on the kind of Othello point, I mean, the objectives I've given here are all differentiable. So in theory, there's no way this could just be implemented quite simply. And indeed, you can see this, this kind of, these gradient-based interventions is basically doing this, but maybe they're not thinking about it in exactly this way.
Thanks, gosh, really interesting talk. I'd have so many questions, but if I have to pick just one, maybe I'll focus on the misrepresentation control condition. I just want to make sure I'm understanding it correctly. I'll go back to a familiar case, BB eating frog, right, with me? So I've had the intuition on that one that we need something like a stronger misrepresentation criterion, that it needs to be a kind of error for the frog. So unintervened on, if we just keep flicking BBs and the frog never detects that it's made a mistake, it just can't represent fly because it doesn't have any. But is it right here that, so the equivalent in that case would be like we intervene on the frog's brain and give it a more accurate fly representation, and now it stops responding to BBs? Would that then be evidence on your view that it all along represented flies? Whereas I would think, no, you're giving it a different representation in some sense. And you still haven't shown that that was a mistake to the frog. What do you think about that?
Yeah, that's a really good question. So yeah, I think we need to separate misrepresentation from questions around indeterminacy of representation. And obviously they're closely related questions. So I think to the extent that properties are highly correlated in the input data, we would expect a lot of indeterminacy with respect to the kind of representational claims we're going to make here. So in that sense, I would expect that any intervention in the frog's brain would end up making it just respond to small black flying things. In that particular example, I would imagine we just have a case where the properties are so tightly correlated that they, in a more general case, this kind of idea of good for the frog. So I guess naturalizing this is one of the big questions in natural organisms. But I think in the case of artificial systems, it's a little bit clearer what the task we're talking about is, in that it's kind of externally imposed by the sort of explanandum, like it's by the task we want to explain. And I think spelling out this explanandum still involves a lot of philosophical work, but that's kind of the hope.
So it seems to me really nice work to take these philosophical ideas and make them much more specific and actionable and even differentiable. I mean, that's amazing. But I wanted to ask you something about very specific on the probe constraints, the correct constraints on permissible probes. So you said, look at all downstream processing, and the probe has got to be something that kind of makes sense that it could be extractable. So I wanted to push you on whether we should look at all downstream processing or just what the next layer could do. So suppose this won't be a real case, but suppose the next layer was just linear, and then there was some non-linearities further down. If you looked at all downstream processing, you'd allow non-linear probes. But really, we want to know what use is being made of this vehicle, this information, by the next layer of processing. So would you agree that that constraint on probe permissibility is really about what the next matrix can do to the current activation?
Yeah, so I completely agree with that intuition. So I think how this would work in practice, and how it indeed does work in practice, is we're probing every layer and every position, and then we're maybe studying something like how the information changes over time. And to the extent the information is present in layer X, but not present in layer X plus K, that means all the processing has happened in those K layers. So definitely that would upper bound it straight away. To the extent the information doesn't disappear in the next layer, it's kind of unclear to me exactly whether we should treat the downstream system in that way as just a single layer. I think in practice, probably that's what that would make the most sense to do, because it's much easier to control for a single layer. But I think conceptually, it might not be doing anything to the information in between layers. It could just be passing it forward or something like that.
Someone in here had a question and I lost them. I know you have one, but you've asked one before, so someone else gets priority. There, no? Well, we can go back to you then, I guess. Sorry, I'll be right over.
Misrepresentation and indeterminacy, because you can't know the conditions of misrepresentation until you've determined the content. So maybe I was just misunderstanding what you had in mind by misrepresentation. And the other thing that when you give your sufficient condition for content, it is quite strange to have a sufficient condition be that the state is capable of misrepresenting, because typically if you've given the sufficient condition, you fix the determinacy conditions. So you should know exactly when misrepresentation occurs. So maybe I'm just confused about what you have in mind by misrepresentation. So it's really just a clarification.
Yeah, of course. So I think there are lots of things to say here, and I think I totally agree with this intuition that there's something deep about the extent to which this can distinguish between indeterminacy and misrepresentation. I think so. I guess what you meant by fixing the conditions, I take to be fixing a successful decoder or something like that. So it's still relative to this whole pattern of activations. I'm not just talking about misrepresentation on a particular input. It still kind of stands in this larger relation to the entire pattern of activations and decoders to it. So it is supposed to be very much tied to how the model is actually interacting with the information across the set of inputs we're interested in. I know that probably doesn't fully answer what you're getting at, but hopefully it gives some intuition.
We could have time for one quick one since she started a little late. Sorry, back there. Okay. Is it quick? Promise? All right.
Yeah, I just think this seems interesting, but I find it kind of hard to like try to understand the math and like this brief presentation. I was wondering if there are like, is there like a paper or some kind of resource that I could like look up and like read up on this?
Yes, there is a paper. It is going to be kind of under review, but if you email me, my email address was I can send you. I'm happy to send you a draft, and that goes to everyone there as well. And I'd love feedback.
So that was not only quick, but also an invitation to a plug. So let's thank Jacqueline again. Next, we have Anders Sogard. He tells me that's his conference name, the Danish pronunciation. My Danish heritage doesn't entitle me to, but he's from the University of Copenhagen. He has background also in the industry, and he's going to speak about how language models view things. Let's welcome Anders.
Cool, thanks. You guys don't hear me either. I'll try to get this out. Thank you so much. So one of the questions of this conference is whether language models are JPEG compressions of huge lookup tables, or whether they in fact have models that are kind of vehicles for inference or thought. Another question is whether language models are in some sense about something, or what it would take to ground them. And I'll try to say something about both of those questions, presenting a very simple experiment. I'll frame this talk as a direct response to a thought experiment in a paper that I'm sure a lot of you read by Bender and Kohler called Climbing Towards Natural Language Understanding. This is the paper in which they present this reincarnation of Searle's Chinese room thought experiment. In their version of the thought experiment, the protagonist is an octopus listening in on a conversation between two people on deserted islands. They're talking through an underwater cable, and the octopus, endowed with a perfect language model, is listening in, training to simulate one of the two. At some point cuts the cable and starts acting as one of the two people. And Bender and Kohler are interested in whether that's going to be possible in the limit, but also whether, if so, that would amount to understanding. I'm not actually going to talk about that part of the paper because there's a lot of problems with that thought experiment, but I'll talk about a second thought experiment in that paper, which is a bit more concrete. So Bender and Kohler write, as a second example, imagine training a language model on just text, so with no associated indications of speaker intent. And imagine that system is also provided a large collection of unlabeled data, and you can sort of train on that, but in a silo, so there's no connection between the text and the images. So they say for the image data, the training task could be anything, so long as it only involves the images. Then they imagine a test time we present the system with models or with utterances, text with photographs, and you ask, the utterances are going to be questions about the images. So things like how many dogs in the picture are jumping, or how many dogs are there in the picture. They are saying that obviously this is not going to be possible because the model has never seen a link between the text and the images. I want to say that's an empirical question. It doesn't really necessarily follow from the fact that these two things are trained in silos, that it should be possible to ask or to answer those types of questions through what in NLP we call visual question answering. And I'll try to present an experiment that I think is good reason to believe that in the very near future, we'll be able to do this. We can't do it quite yet. We can do it with very minimal supervision, but without any supervision at all, we can't do, but it should be possible very soon, and I'll try to convince you. I take inspiration from work in something called unsupervised machine translation. So this is a sub area of machine translation. So people doing things like Google Translate. Normally, when you do that, you try to learn a function from one language to another, and you use supervision from human translations. So you induce a function from, say, German text to English text, but you adjust your parameters so that you simulate human translations. Now, in unsupervised machine translation, you try to do that with no human translations in the loop, so with no links between, say, German and English. Now, how is that possible? Well, what people do is that they look at the word embeddings of language models. So you train a language model for German, and you train a language model for English, and then you look at the geometry of the word embedding space. So you basically plot your vocabularies as point sets or point clouds, and you look at their shape, because it turns out that at least for reasonably related languages, vocabularies have similar shapes. So you can think of these as just sort of clouds that are floating around in space, and they have a geometry. Now, what you can do is you can scale and rotate and translate these clouds so they align in the best possible way, just like you do in point set registration in computer vision. And it turns out also that if you do that, then at least for related languages, the alignment is so precise that you can extract bilingual dictionaries from those alignments. So empirically, something like 3 and 4 words you're going to have right next to its translation equivalent. So I want to transfer that idea to this case where in the Bender and Kohler example, you have a language model on one side of the fence and you have a computer vision model on the other, and ask whether the same thing can be done for language models and computer vision models. To get translation rolling, you need a bit more, because at this point we only have word by word translation. So you need to basically bring the language models back in the loop and do code training of 2 systems in both directions to get the thing rolling. But we can ignore that because we only need for now, only need to establish the links to get about this. Okay, there's an important lesson from this literature that I want to tell you about. So doing this in an unsupervised fashion with algorithms like generative adversarial networks is possible if the spaces or the geometries are very similar. So what this means, and here's some results from an old paper on unsupervised machine translation. Basically, if we can do it such that more than half of the words end up next to their translation equivalent, unsupervised algorithms tend to work. If not, they tend to fail. And this is because if there's no obvious solution to this alignment problem, there's just a lot of local optima that you can get stuck in. But it seems that there's a threshold around kind of where about half of the words align with their translation equivalent, and then unsupervised algorithms work as well as supervision or minimally supervised solutions. I'll get back to how we do that. Okay, so basically what we do here is we do what Bender and Kohler instruct us to do. We have a bunch of images, we have a bunch of texts, say sentences, we have a vision encoder and a text encoder. There's no interaction between the two. We get the image embeddings out, we get the word embeddings out, we look at the spaces for some vocabulary, and then we do alignment based on, in our case, minimal subvision. So this would be something like maybe 100 words. Then we evaluate whether we're picking out the right things from this alignment on held out data. Okay, so this is a minimally supervised setup for bilingual dictionary induction, except that we're talking about images and words. We've done these experiments for a lot of different models, and this is an unsupervised vision encoder called MAE, 3 different sizes. And this is the performance of 3 different families of language models. So along the x-axis of each plot, you have language models of different sizes. And as you can see, so the lower set of lines here, that's precision at 1 score. So this is the number of words where we going from images to the language, and the vocabulary here is 70,000 words. So the kind of random performance here would be 1 over 70,000. We see that for the best models here, which is GPT-2 large sized models roughly, about 10% of the words or the images end up next to the word that happens to be the label in the ImageNet data. If we're a bit more loose in the evaluation and we just ask whether the word is in a neighborhood of 10, which is roughly what corresponds to a synonymy class, for example. So for car, this could be car, automobiles, vehicles, etc. About 30% of the words do that. And if we're even more loose and we just ask whether the right word is within a neighborhood of 100, so this would correspond to something like a fine-grained semantic category, we see that about 60% of the words do that. Okay, so for 60% of the words, we can tell what the semantic category of the image is, if you like, with very minimal supervision. The most important thing about these plots is that we see a convergence, right? So the bigger the models get, the better the results. The bigger the vision encoders get, the better the results. The better the language models get, the better the results. There's still a gap to what was the break-off point in unsupervised machine translation, which would be a precision at 1 score of about 0.5. That's 0.1. So that's quite a gap, but there's certainly convergence toward that. And even if we can't do it in an unsupervised fashion, this still points to the fact that these models are learning the same structure. It's just that we can't do the mapping right now in the complete absence of supervision. Here's some results with supervised vision encoders, SecFormer models, and ResNet models. These are supervised, so you could maybe argue that introduces a bit of a bias, but point is the results are the same, and you see the same convergence phenomena. Of course, there's you can do a lot of error analysis on experiments like this. Clearly, some words are polysemous, and that affects performance. So mono or words that only have one sense are easier to do this mapping for. Also, dispersion in the images is a factor. So if there's low dispersion, we do better. So that's only a natural. We're basically extracting static embeddings here from the language models, right? So we're not capturing context in any way. So all of that is sort of making, I think, the results even more interesting, because the results from just a moment ago were across the board. Now, of course, you can ask whether there's sort of biases creeping in, or forms of contamination from the inductive bias of the algorithms, or maybe the fact that we evaluate this on ImageNet names. So we can do the same experiment with other target spaces or other source spaces. In this case, I've been doing the same experiment with the BERT family of models, and then mapping into the big graph space. So big graph is a graph embedding of Wikidata. So this is a knowledge base that's supposed to say something about how we like to organize the world. You get exactly the same convergence phenomenon here. And I think what all of this is saying is just that the reason that we can align the concept level representations of language models and vision models is because they're about the same thing, namely the knowledge that we also put in Wikidata. And I think in some sense, that result was already in that first thing I talked about, namely the unsupervised machine translation. Because why would a language model for English and a language model for German represent concepts in exactly the same way? If it wasn't because English and German are being spoken by speakers who speak about the same thing, namely the world. So I think in some sense, there's not bulletproof proof, because of course languages are related, and there's all sorts of things, all sorts of counter arguments, but I think this is at least suggestive of the fact that languages or language models are already, or that you can see in those experiments already that these language models are picking up on structures of the world, or the world as we think of it. That's it.
Okay, who has questions for Andrews? Okay. And would Tony, if you want to start setting up. If he's here, I haven't seen him.
Hi, really cool work there. Have you tried any unsupervised alignment algorithms? One could imagine, say, looking at the within pair similarity of different labels and deriving a cosine similarity matrix from that, and sort of just trying to align the visual elements in the same way without the use of any labels or paired examples at all. Yeah.
Right. Yeah, we did. So the problem with we've been playing around with GANs to do this, and the problem is that it's super initialization dependent. So if you sample from a space that's not too far away from the correct solution, an unsupervised algorithm will get you there. But if you sample or initialize at random, the chance is very low. And it's just because there are too many kind of bumps on the road. But it's a great question. And certainly I think, so my whole argument is that I think the structural similarities are not good enough yet that we can do that with the existing algorithms. So you can think of that as a problem for the existing algorithms, or as a problem for the language models and the computer vision models. But I think either way, we'll get there.
So the slide with the picture of the bicycles, it said something about categories. So just a clarification, have you got all of the pictures organized into categories before you start?
Right. So we're evaluating, the way we're evaluating in this experiment is that we take ImageNet images. So, and then we ask whether the alignment will give us the label for the image that we're currently looking at. So we sample an image from the image in the data set, and we ask whether the alignment is going to tell us what the label of that image is.
I'm not sure if I understood your answer. My worry is that if they are already sort of put into clusters, then there's some semantic information getting in just sort of without the label.
Right. So the vision encoder is unsupervised, so it's not actually seeing the labels. Right. So we only see the label at test time in the unsupervised setup, and then the minimally supervised setup, we have we see the labels of a few or a few other categories than the ones that we're evaluating on. Does that answer your question? And also training on ImageNet is not, so we can do this with unsupervised vision encoders that are not trained on the ImageNet set of images. So I don't think there's any risk of contamination or bias.
Oh, here we go.
Thanks. So Descartes, one of the things that kind of he proved was that he showed that we can think about algebraic geometry and like visual geometry. There's like this interesting kind of correspondence between these two things. So we can have an algebraic representation of geometry. We can have visual representation of geometry. And so if you kind of want to kind of extend his project to what is happening here, maybe we can say these models don't really see the word. What they're seeing is that they're finding correspondences between visual representation of the word and the analytic representation of the word. And I think we can have like a nice kind of like background story similar to what Descartes did. So then if we kind of push that idea forward, is that these models don't see the word. They're just seeing representation. They're seeing connections between different representations of the word. What do you think about that proposal?
Right. Yeah, that's an interesting suggestion. I think, I mean, clearly what at least the minimally supervised experiments show is just that there is a second order isomorphism here that is equivalence from the perspective of a neural network. In terms of seeing, well, I mean, clearly humans are endowed with the capacity for doing point set registration. Whether this is what enables, say, colorblind or blind people to infer what the color blue means, I guess it's a question for cognitive scientists and not me, but it definitely is suggestive for how that could come about.
Yeah, thanks for the talk. It was really interesting. I wanted to maybe push a little bit further on this idea of the image data set having some built-in structure to it that could be at play here, because even if you're not using the labels, you're still, of course, using pictures that were taken by humans that probably point to things that have labels, because that's how humans are viewing the world. So I was just wondering if you thought about like, if you, how extreme you could take this, if you could really have an image set that was kind of random and not guided by human concepts, if you think you could still get some sort of alignment out of it.
Right. I mean, that depends. So some of these models are trained on ImageNet, but we can do the same experiment with models trained on just random Flickr images. Now, whether that still comes with a bias, of course, I mean, but so does language, right? I mean, there's a tokenization of the world that's implicit in all of the data here. And, you know, that's part of the bootstrapping we have to do as kids, and we're sort of jumping in the middle of things here. And I'm not sure there's a way around that problem.
We have time for more questions.
This is very striking, but I wonder if you can speak to whether the structure of the space is used by either one of the models, especially the one that's got a task, the language model. So, I mean, it's reflecting something that it can pick up on the world, but we've seen in lots of earlier talks, there's a big interest in whether that's being made use of in order to perform the next word prediction task.
Yeah.
And have you got data that would speak to whether aspects of this structure are being made use of?
Right, that's a great question, thanks. So yeah, we got a couple of papers on, one is in the cross-lingual space, whether this isomorphism is correlated with downstream performance. And that's a clear yes. The other thing is, so Fintan had these examples with the analogies. And if you do analogies in the limit, you get isomorphism. And one of the things that we've seen is that if you do analogy training, so you basically train your language models to optimize for this analogy. So you just, you know, you take Wikidata and you generate all the analogies you can, and you use that as training data. Your language models become better at downstream tasks too. So I think those two things combined is suggestive that yes, the language models are actually using this geometry as a vehicle for thought or inference, whatever you like to call it. Sorry.
Hi, I had a question about the experiments. Are the dimensions of the image and word spaces pretty similar? And would this still work if they were like vastly different?
Thanks for asking that question, because I promised to tell you guys about the supervised alignment methods and I didn't. I forgot that. And I can do that now. Yes, so we do two different things. One is Procrustes alignment, in which the dimensions have to be similar. And to get that, we do PCA of one of the two spaces first. In the other setup, we do just linear regression, where we have a linear regression model for every dimension of the target space. And then you don't need that. So the answer is, no, they're not the same dimensionality. You can do PCA to get rid of that problem, but you can also just do linear regression and then it's not a problem at all.
Hey, thanks. This is very interesting. I was just wondering, I imagine that the conceptual spaces of vision and language might not be directly overlap or like completely overlapping. I was wondering if you can hypothesize where those might be most similar, and also like more interestingly, where they might be least similar for like what concepts.
Jesus, that's a difficult question. I mean, I'm not going to give you a good answer to that, but I can point to those results saying that dispersion is a phenomenon, so it's a source of error. I mean, the nice thing about language is that it's, at least presented to us in written form, it's discrete, and that's a huge advantage. And I would think that has sort of trickle-down effects. I know it's a lousy answer, sorry about that, but it was a difficult question.
Actually, related to that, I'm wondering if you find there are certain kind of basic concepts that really help in the alignment. I mean, one obvious thing is space, right? Spatial relations, bigger than, smaller than,
right?
Structural things that go across all kinds of common environments. Is there any indication of that kind of thing playing a role?
We are about to do some more experiments in which we sample vocabularies of different semantic categories, and I think that would tell us more about that. We know that, I mean, I think I missed out on the panel discussion yesterday, but I think Ellie talked about some of the color stuff that we've been working on. There's other places in which there's a sort of there's a physical space too that we can map onto, and I think it's very likely that it's going to be easier to do it for those domains. So we've looked at geography. We have some students did a paper called like, "Do language models know the way to Rome?" or something like that. And yes, we do see alignments there too.
Still got, oh, here's somebody. Sorry, where'd you go? There.
Hi. Sorry, my question is related to that gentleman's question. It makes sense to me that German and English would have approximately isomorphic semantic geometries because the models are learning language as it is used. So the assumption of this project would seem to be that images as they are used by humans would be approximately isomorphic to language, but it seems that at least naively, it seems that humans are likely to use images in different and often complementary ways to text. Why would you, I mean, there might even be some duality, I guess, in the representational spaces. Why would you expect them to be approximately isomorphic?
I wouldn't. And I think you're right. There's duality in the space. And we know that from disinformation, from reviews, where like often there's duality. But I think that we're looking at representations deep down in these models where things are very compressed. And I think there's a lot of use that's sort of filtered out in the process of building these. So I think there's a lot of ways you can sample your data and still end up with the same lexical representations if your model is big enough and it's trained for long enough. So I think we're distilling something that's less sensitive to that phenomenon.
Having been tasked with running these lightning rounds, I can't resist trying to actually be on time. We might actually make it, which I think would be a first in my experience. I don't know about anyone. So thank you. Let's thank Anders.
Great. So hi, I'm Tony and this is Sed, and along with our other two co-authors who are in the audience, Mitchell and Ho-Kyung, we're going to talk to you today about whether deep neural networks have concepts or not. So like we were introduced, we're a group of first-year grad students at MIT BCS. And like as first-year grad students, we obviously have an incomplete view of the landscape. Or maybe I should say, like, as first-year students, we obviously know everything there is to know about concepts, and Actually, maybe you guys should just like sit back and let us tell you all the answers. So in many ways, I think the structure and the goals of this talk parallel the ways in which we came to and came at these questions. So the four of us are all interested in things like concepts, but we come from quite different backgrounds, such as computational neuroscience and, for us, computational cognitive science and philosophy. And so when we started talking about these topics, we often found that we needed a shared language or a common denominator to start from. So given the rapid success and excitement surrounding ChatGPT and other LLMs trained with human feedback, I think a lot of people have started asking if GPT-X is like intelligent or if it's thinking. And I think it's natural to first start asking whether these systems have concepts or not, especially given the long history in cognitive science and philosophy that takes concepts to be the fundamental building blocks of thought. So maybe when we ask this question, it might be good to start with a system that's simpler and potentially easier to understand, a visual classifier and pattern recognition system like AlexNet. So we could ask, does AlexNet have concepts? Well, to know, we would need a working framework that would be able to formalize what concepts are in neural networks and in a way that we can empirically verify. So this motivates our starting point. We're going to take concepts to be manifolds in neural latent space. And for the purpose of exposition, I'm going to use vision, but this approach extends to other modalities like language and text. Formally, manifolds are defined to be these objects that are locally homeomorphic to Euclidean space. But for our purposes, we're basically just going to take them to be clouds of points with some rough topological structure. For example, you could take a picture of a dog, and that would map to a particular point in the intermediate or hidden space of a neural network. A different image of, say, a different breed of dog might map to a different point, but it's still an image of a dog. And so the set of all points corresponding to images of dogs form this dog manifold, which you can think of as a very extensional characterization of a concept of dog. So we're going to add the additional requirement that these manifolds be separable from each other. So that is, the manifold for dog is separable from that of a cat. And that's a key property that allows for successful classification. And this is a really common view that's often held in neuroscience and sometimes in deep learning. And this is partly motivated by the fact that this framework is really directly applicable and easily formalized in neural networks. Right? And a lot of the concept learning or work on concepts in neuroscience and some parts of deep learning often focuses primarily on very concrete and perceptual concepts, which are easier to formalize in this paradigm. So under this framework, we might say AlexNet probably does have concepts, but this is mostly because this concepts as manifolds framework focuses primarily on discrimination as its relevant behavioral property of interest, right? And as we know, this is something that neural networks are great at. But I think in this way, concepts as manifolds also gets at a common denominator among theories of concepts, namely that while these theories often disagree on exactly what concepts are, most of them do agree that any conceptual system should be at minimum able to discriminate between valid and invalid instances of a concept. But on the other end, human conceptual systems are far, far richer than that of a CNN like AlexNet. They can exhibit, for one, a much wider range of behaviors, such as analogical reasoning, imagination, and planning. And what's more, our conceptual system often encompasses more abstract concepts like fun, like good, belief, is, and 9, just to borrow a few examples from the debate last night. And it's not a priori obvious how we would formalize these more abstract concepts as manifolds, or whether they even have a manifold structure at all. And so for those concepts, we won't have much to say here. Finally, the point that I might make is that it's also intuitively clear that this is not enough, right? The reason that GPT-3 is better than GPT-2 or GPT-4 is better than GPT-3 is probably not primarily because its concept manifolds are more linearly separable in high dimension. That doesn't seem quite right. And so for the remainder of the talk, we'll use this motivation to take a first step towards two goals. First, we're going to draw on some hard-won insights from psychology and philosophy to name several properties that our framework is currently missing, but should capture. And some of these properties are going to be global ones of conceptual systems as a whole, and others are going to be properties of most or all of the concepts within this system. Importantly, we want to stress that we're not proposing a new theory of concepts here. And we also acknowledge that this list is also missing the mark in many ways as to the full richness of human conceptual systems. For us, we just see it as a way to formulate a shared ground that any characterization of conceptual systems and neural networks should aim to capture. So in that spirit, our second initial step will be to propose a few basic ways that this concepts as manifolds view can begin to account for some of these properties. And with the obvious caveat that this is really preliminary work and a lot of these formalisms, or maybe all of them, will be insufficient in many ways. So to begin with, a conceptual system should be generative. It should allow for sampling of instances of the concept. So take an example of something like a dog. I could imagine a mental image of a dog. I could imagine the sound of its bark, or I could imagine the feeling of its fur under my skin. And although this concept as manifolds primarily focuses on separability and discriminativity, we could readily extend it to include generativity by specifying a way to sample from our concept manifold, right? This could involve like placing a probability distribution over this manifold, or just some way to smoothly traverse the manifold and stay on it. A clear illustration of this is with variational autoencoders that can be trained on MNIST digits. What you find is that the digits often form separable manifolds in the latent space, and you can traverse these manifolds to sample instances of digits. So the next property is context sensitivity. We want concepts to be flexible and not rigid. So for example, if I won $1,000 or $1 million, I might say I'm rich in both cases, depending on the context in which I won that money. And to use another example from the debate, whereas most times I might perceive that leaf as a leaf, there might be contexts in which I see that leaf as an umbrella, namely if it's raining. And so when we started, we presented manifolds as these sort of static things, but this doesn't allow for context sensitivity. And so what we really want is when we project inputs onto our latent space, into manifold space, we should allow for the projection to be a function of both the input itself and also its surrounding context. This can be the surrounding words or conditioning on some goal or other things like that. And in modern large language models, this often comes for free as a consequence of the architecture.
Okay, now I will move on to some properties of concepts that are harder to define. And the first one is abstraction. A concept should be abstract, robust, and general. Intuitively, this means a conceptual representation should extract some essence from the appearance. And for example, we can all recognize all the image on the left are dogs. And we also know that the relation on the right-hand side should hold true regardless of what type of argument it takes. So this kind of invariance is very important for abstraction. And how might we formalize this in the concepts as a manifolds view? We suggest that the manifold should be closed under some irrelevant transformations such as rotations, viewpoint shifts, noise, and irrelevant context. That is, if we take a picture of the dog and then rotate it, it should stay on the manifold and not leave it. So as illustrated in the picture, repeatedly rotating the image may shift around the representation of the input, but never in a way such that it's no longer in the manifold. Next, we consider the property of concepts that it should be relational. A conceptual system should capture the relations between concepts. Here are two examples of such relations. On the left, as Ned has discussed in his famous work on conceptual role semantics, force is not really defined in terms of mass and acceleration. Rather, the equation F equals ma is an equation that specifies the relations between force, mass, and acceleration. On the right, certain concepts naturally form hierarchies, such as a cat is an animal. And within hierarchies, we can also talk about similarities, such as cats are often judged to be more similar to dogs than birds. In order to bring in a notion of relationality into concepts as manifolds, we need to impose some between manifold structure to specify how different concepts relate to each other. This can be done by imposing a similarity function or a distance metric on this overall space that specifies, in some sense, semantic similarity between two concepts. Additionally, we should have compositionality in the conceptual system. A concept should be able to be combined with other concepts. Furthermore, the combined concepts meaning should be determined by its constituents meanings. For example, the concepts red and dog can be combined to form red dog, and we can apply a negation operator to a proposition to form a new proposition. In the context of having a manifold view of compositionality, we specifically consider the compositionality of Boolean operators. Under this view, Boolean operations correspond to set operations on manifolds. That is, the manifold of red dog is simply the intersection of the manifolds for red and dog, while initially the concept of the manifolds view holds that manifolds should be separable. We explicitly revoke this assumption here to allow for compositions. But again, this is a rudimentary notion of compositionality and does not capture its full richness. So finally, here are some other important features of a conceptual system that have been long discussed by philosophers and cognitive scientists. But at the moment, we are also uncertain about how exactly the manifold view of concepts could or should account for these features. Intentionality is that a conceptual system should be about things in the world. It's also sometimes called aboutness. Also, it should be internally consistent, which is arguably what today's GPT type of system really need to improve on. And a conceptual system should have a rich causal structures, which can support robust hypothetical and counterfactual reasoning. As I just mentioned, an important question is how we could formalize these properties in neural systems. So to summarize, if we are interested in whether neural networks have concepts, simply discriminating of being able to decide decode information is not enough. And we want a formal characterization that we can empirically test. We propose a non-exhaustive list of properties that any conceptual system should satisfy and give a first pass attempt at how some of these properties might be partially operationalized. And some of these properties are incredibly important and of philosophical and psychological interest, but it's not clear how they might be formalized. Given that we do not have a complete theory yet, we also asked GPT-4 about its opinions. So specifically, we asked GPT-4 what it thinks about whether deep learning models such as AlexNet, GPT-3, and DALL-E2 satisfy the list of properties we talk about here. And we asked it to give letter grades like A, B, C, D for each. And this is a prompt we provided. And here is the answer it gives. So we think this is pretty impressive, and we would like to invite you to think about how you would judge the systems, and where do you think people would disagree the most? Can some of these properties define in terms of others? And what other properties are missing from this picture? Or is this even the right framework to think about concepts in neural networks? So at the end of the day, we would like to have a satisfactory theory that explains to what extent the systems have concepts and what their conceptual systems are like. So for acknowledgement, we would like to thank Josh Tenbaum and members of the Kokusa Lab for helpful comments. And we would like to thank you, the audience, for your attention.
Who's got questions? Oh, one up there, and one down here. All right. Can you pass this up?
Thank you. Well, one of the rightful critiques of earlier models, particularly convolutional networks, had to do with the cherry picking in reporting results when it comes to capturing those concepts, where, you know, in practice, many of those concepts wouldn't be captured, but wouldn't be reported in a paper or so. And this seems to be alleviated in later models, particularly when it comes to text-to-image models, where the outputs are clearly capturing some concepts to a better extent. But these are more, I'd say, like opaque models. They're larger and less interpretable. So where do you think folks' attention should go when it comes to judging the ability to learn concepts? More on the output, if it's satisfactory enough, or the inner workings of the system?
Yeah, I think that's a great question. And I would say that like behavior matters a lot. And in particular, probably a lot of these properties are going to be falsifiable from behavior. But I think that we explicitly tried to articulate a partial, very partial theory in terms of representations because we're interested in trying to characterize not just behavior, but actually like how the inner workings are organized. And I think this can be helpful for like, you know, both interpretability, but also when we try to think about how we might design better systems. These are basically properties that are important beyond just knowing how the system works or like what input-output relation it does.
Yeah, just to add a bit, I think that's a great question and really fits the theme of our conference here. And I think some earlier speakers also talk about like whether like behavioral tests enough or like we really need the inner workings. And on this point, like we internally also had a lot of discussions. So maybe one view could be like extensive, like carefully designed behavioral tests is kind of enough to answer the yes/no question, but really to get a theory that can do explanatory work, we maybe really need to look at the inner workings.
Yes, thanks. So one thought about the compositionality criterion is that you might want to go for something more ambitious, more like manifold interpolation, where you're actually creating a new manifold by combining the two. And this has been like, you know, in cognitive science, sometimes the criterion has been like, if you combine two concepts, maybe the composition has some properties that neither of the components has, like industrial tomato might be artificially ripened, or pet chimpanzee might have a diaper, whereas chimpanzees don't normally have diapers and pets don't normally have diapers. You get the idea.
Yeah, right. I think that's, again, like a really great point. And this is actually something that we've been thinking a lot about. We articulated a very modest notion of compositionality, but we've recently started thinking about how we can define compositionality in ways that aren't just logical, and also ways that in which there are like emergent properties that aren't present. And I guess just to make an allusion to it, like one of the ways we've been thinking about it, a way to define a manifold is as the set of zeros of a function. So like you can take a bunch of points, look at all the points that map to zero under a function. And this often leads to like a quite interesting picture of compositionality where each manifold has a function, is induced by a function. And if you take two manifolds induced by two functions and you combine their functions by some like higher order function, you get another manifold that can sometimes be quite different. And this is a view that like strictly generalizes the account that we put here. And this is obviously very, very preliminary, so we didn't even put it on the talk, but like I just want to acknowledge that we've been thinking a lot about these issues as well.
So this is following up on this, and also something you said about context sensitivity. So your suggestion for context sensitivity was deforming a manifold, and this kind of compositionality would lead to a deformed manifold. And that looks all empirically plausible, but one of the things we were supposed to get out of compositionality of concepts was that concepts make a stable contribution to the determination of the meaning of the complex. Are you just happy to give up on that? And what are the theoretical costs of giving up on that?
Yeah, right. I can say just a little bit about this. This is actually something that we've grappled a lot with, because you get a lot of flexibility with context sensitivity, but you also sort of lose like an objectivity of like there being like a place in the space that corresponds to dog. And to be honest, we don't have a great answer for that. Like, I think our view is that you could have, we started with like a context insensitive language, like a network, and then you add in context. And then what happens is that the manifolds sort of get shifted around, but I think it can still be helpful to start with the wrong assumption that there's some region of space that is like semantically interpretable and stable across contexts.
Nice, that was very nice. I'm wondering about whether you are thinking about the capacity, when it is implemented in the network, you can have, I don't know, infinite ways of interpreting an image, while can you have infinite configurations of the neural network, you know, of the activity of the neurons?
Yeah, right. This is something that like, I think the two neuroscientists among us know a lot about, but there are definitely like analyses of so-called manifold capacities, which is like in a hidden layer of a neural network, how many manifolds can you have that can be like linearly separable, which is a slightly stronger criterion. And what you find is that it often changes and it fluctuates throughout the neural network, the layers of a neural network. So yeah.
A question about like vague concepts or concepts that have
fuzzy boundaries? Does the manifold have a fuzzy boundary, or like what's the math behind that?
Yeah. A manifold does not have a fuzzy boundary, but one of the things that we like are talking about in empirical settings, you almost always assume that there's some true manifold, but everything is like generated from that manifold plus noise. And so there can be a sense in which like classification or membership is a fuzzy thing just based on like how much noise you think was contributed to like when that instance like arose. But you're right that in like the formal definition, like a manifold is just an object. It's like not a probabilistic or fuzzy entity.
Hey, do you mind going back to the table? Yeah, great. I'm curious how you think about learning concepts in the context of this table. So someone who fails to recognize a particular dog breed as a dog, right? We don't say, oh, I guess they didn't have a concept of dog after all. Or someone who didn't know that, right, dogs were domesticated from wolves, right? Again, like, yeah, they're missing something, but again, it doesn't endanger their having a concept. And the question of whether someone has or doesn't have a concept is probably an ill-posed question. But do you imagine, so there's a developmental process, do you imagine a person or a machine, right, getting kind of better in parallel on all of these properties? Is there some ranking, right, some order that you think is likely to be followed?
Yeah, I think on the learning issue, like in early version of this, we actually have like a learnable or like supportive learning is being one of the properties, but also it's kind of like too hard to say like exactly what it means like in this kind of mindful view. But I think, yes, certainly, I think even like humans, like each of us may have like different like levels of like knowledge or experience of learning. So like, I think we all have like very rich conceptual systems, but like through learning, we can even have like even potentially even richer ones or like discover new concepts. So I think these are like very important things to like further investigate. But in terms of like a ranking, I think I would say that like a lot of this together, like if you have like the more you have, like maybe like the more supportive learning the system gets. Like you can imagine having compositionality really allows you to learn like a more like complicated concept easier. And like causality might use like you can think about, oh, what didn't happen, so you can like offline think about, you know, like what you could have done differently, and maybe that's another kind of learning process.
Yeah, and maybe one really quick point that I would make is that Seth alluded to this. Maybe some of these properties are not actually like totally different, and they arise from something deeper. And it could be the case that when you acquire that deep understanding, you suddenly get 3 of these properties at once or something like that.
Let's, well, I want to register first. There are a few other questions in the queue, so that I hope you hunt them down later. I'm sorry we didn't get to you, but let's thank our speakers and